Okay, everybody, let's talk about section 6.2, areas under the standard normal curve. And what we want to do is we want to get more of a sense of how do we go about finding probabilities that are associated with the standard normal curve and the area underneath it. Well, there's a few properties that you have to know of. First of all, the basic properties of standard normal curves say this. First of all, the total area under the standard normal curve is 1. That's true of any density curve. That's true here as well. Now, the standard normal curve extends indefinitely in both directions. In other words, we typically don't think of it as having an endpoint, and that the curve itself approaches but never quite touches the horizontal axis as it does so. So there's always considered to be some positive probability, even if it's a very, very teeny tiny small number that's almost indistinguishable from zero. Still positive. Property 3, the standard normal curve is symmetric about 0 of the curve to the the part of the curve to the left of the dashed line in the next figure right here, 6.14. We'll show it here. There it is. The part to the left of that z value, to the left of z, right, is the mirror image of the part to the right of it, right? So if we go to our curve right here, if we pick the varies to the left, we have a mirror area to the left, right? And that's really helpful because, well, what can we do right here? We can actually see that we would take 1 minus the area to the left of z, right? Because remember, if two probabilities add up to 1, then the probability to the left would equal 1 minus the probability to the right. That's kind of cool. All right, here's the fourth one. Almost all of the area under the standard normal curve lies between -3 and +3. Interesting. All right. Well, what does that mean for us? If we were looking at the standard normal curve, we did this in our last example. We looked at the table. Here's another view of the standard normal table, this time for our positive z values. If we wanted to find the area under the curve, the way we're going to do it on the table is that we're going to go to our first column right here, and that's going to give us our z value to the 10th. And then along the horizontal line up here, these rows, these columns represent our 100th digit. So in this example right here, we have the number 1.23. So for a z-score, if we have a z-score, oops, let me get my pen. Come on, pen. If we have a z-score equal to 1.23, then what we're going to do is we're going to go to find 1.2 along the first column right here, the 100th digits, the 0.3 along this column, and look for our resulting digit. And this represents the area under the curve, under the standard normal curve. Now, the other method for doing that is to do so in Excel. And in Excel, we have a command for the standard normal distribution. Let's take a look at it right here. For the standard normal distribution, the command goes like this. We use the command equals norm.s.dist, and then we enter in whatever our z value is, and we enter in true to represent the fact that we are dealing with a cumulative area under the curve. We want a cumulative area, so this is the way we write this command. So let's say that we wanted to find the one for 1.23, which was just what we looked at in our table right here. Here it is, right? We looked up 1.23 in the table. Well, Excel does the same thing very, very well. We go equals norm.s.dist, and we can select the command right there. And we can put in our z value of 1.23. And of course, we could select true or false. We want true. And there it is, 0.8906. If we go back to our table, what did we see? 0.8907, rounded up. Sure enough, there it is, right? It's the same thing, 0.8907. There we go. All right, so this is pretty good. We can use Excel to get a lot of these values for us. Now, again, mathematically, working with these areas, here's the way that we do that. If we wanted to find the area under the standard normal curve, what we get directly from the table and from Excel is the shaded area to the left. So this is automatic right here. If you're using Excel or if you're using the table, either one, right, we automatically get this area to the left. So there's not a lot of mathematics here other than looking up the value on the table or putting it into Excel to get it. The rest of it is not automatic. We have to do things to get it, right? So what we would have to do, let's say that we're interested in the area to the right. We say, okay, what is the probability of finding a value greater than this value of z? The way we're going to do it is that we're going to have to take 1 minus this area that we got over here from the table, right, or Excel. Right? Now, the other case, of course, is that if we have two different z values, what do? Well, the way we're going to handle it is this. We're going to find the area that is to the left of the larger z value, which is the area of everything to the left of that, and we're going to subtract away the area that's everything to the left of the smaller z value. All right? So when we subtract those two values, right, the area to the left of z2 minus the area to the left of z1, we're left with the area in between, right? So that's the way that we're going to do this. And I'll illustrate this with an example. Okay? A bone mineral density test is an example of a type of situation where we actually use a z-score, right? It's a measure of the bone density and tells us how likely it is that a bone is going to break, how fragile, or get osteoporosis or different diseases like that of the bones. The population z-score is normally distributed with a mean of 0 and a standard deviation of 1. So let's say that we found somebody and we said, well, what is the probability that we're going to find somebody with a bone density reading less than 1.27? Well, what we would do is we would go to Excel and enter in our formula right here, or go to the table and find 1.27 there. If I do this in Excel, let's try it out. In Excel, I would take my norm.s.dist right here. Here it is. I would put in 1.27 and true. And there would be my probability, right? So that's the way I'm going to get that one. Here we go. So right here we would see that 0.86437, oh, well, here's one for 1.10. Pardon me. Let's put in 1.10 instead. Here I am changing the example in the middle. But all right, we'll go with this. So what does that mean? Well, that means that the area to the left of 1.10 along this horizontal axis, which represents our z value, is 0.8643. Well, that's useful because we can now tell what's going to happen there, right? We could say that 86.43% of the population would have a bone density less than 1.1. How about the bone density greater than 1.1? Well, what we're going to do is we're going to take this value and we could actually subtract 1 minus. Right? We could actually subtract 1. Get my pen. Come on now. 1 minus 0.8643 to get the area underneath this part of the curve, right? Because anything that's to the left is going to mirror anything that comes off to the right. Right? So if we wanted this right-hand area, that's what we would do. And so in Excel, we would type in a formula just like that one. We could say 1 minus whatever we get from our normal distribution at 1.1. That's 0.1357. That represents the area to the right. If you add 0.8643 and 0.1357, you should verify for yourself that this adds up to 1.0, the total area under the curve. All right, what about a bone density reading between negative 0.05 and 1.5? Well, just like anything else, what we said was we're going to subtract the two variables, right? We would subtract whatever we get from the bone density from the larger one, 1.5, minus the one that we get from the lesser one of negative 0.5. In Excel, here's how that looks. You'll note that what I did here was that I took my very first probability, which is the larger probability, and I subtracted from it my smaller probability right here. So this is our smaller probability. And it's like as if we're just saying, okay, for that smaller probability, we subtract this away from the larger probability, and we get a total probability of 0.6247. So 62.47% of the population would have a bone density less than or between negative 0.5 and positive 1.50. Now, there is some specific notation that we can use to quantify all of this. We use it, it's called Z alpha notation. The Z sub alpha is used to indicate the score that's associated with an alpha area that's to the right on the standard normal curve. I'm going to read that Z sub alpha, or Z alpha. All right, so what does that mean to us? Like, if we went through and we wanted to find the Z alpha, we could actually work our way backwards now and figure out, well, if we knew what the area was, we could look it up on the table and find the Z associated with that area. And in this case, let's say the area is 0.025. Well, in this example, then the area that is to the right would be 0.025, the area to the left 0.975, right? So that's associated with 1.96. Here's another example. We want Z.005. Well, the way that we could do that is this. We could actually look it up on the table. Another way of dealing with it, by the way, is this. We find it's 1.645. Here's what we're saying. This area underneath the curve, they're saying is 1 minus 0.05. So what could we do? In Excel, there's a way to do this, and I'm going to show you here. Here, let me show you the Excel method for doing this. If I wanted to find the area associated with the Z alpha, right? So let's say I want to find Z of 0.05, right? That was our last example right here. The way that I'm going to do that is I'm going to use another formula called norm.inv, N-O-R-M, and you'll see this selection right here, norm.inv or norm.s.inv. I'm going to hit norm.s, that's a standard normal curve, INV, and we enter in the probability that we're interested in. So in this case, it's 1 minus 0.05. And if we enter that, boom, there it is, 1.64485. Well, in our slide, we said that was 1.645. So yeah, that's right on the money. So we can use that command norm.inv to find this. All right, more to come.